just didn't have the same properties as the old ones. So the firm called in a metallurgist to investigate. And we're going to look at the questions he asked and especially the techniques he would have employed to solve this particular problem. This is one half of a medium-sized set of mill brasses. This flange and these recesses are used to locate the brass within the rolling mill frame. This is the bearing surface, and the roll ends rotate on this surface, and so this is the area that's subject to wear. Now, the first thing the metallurgist would do would be to check if the chemical composition of the new and the old bearings were the same. And he would do this by taking samples from a variety of locations and sending them off for chemical analysis. These are the results of the chemical analysis. The old bearing contained 92.5% copper and 7.5% tin, and the new bearing contained 92.7% copper and 7.3% tin. So there's no significant difference in the overall chemical analysis of both bearing materials. The next thing the metallurgist did was to examine the internal structure of both the bearings, and in order to do this it's necessary to take sections. The section which reveals the most information with the least amount of effort is a transverse section. This enables the metallurgist to examine the internal structure of the bearing material, both in the body of the bearing and also along the running surface. Samples are taken by hacksawing out suitable samples from the bearing in question. Here's a smaller bearing, but the principles are exactly the same. And here's a transverse section. In order to preserve the edges of the sample, it's necessary to mount it in a thermosetting plastic. This is cured by applying a moderate pressure and temperature to the thermosetting compound. Once set, the pressure can be released and the temperature lowered. The sample is then removed from the mould, and now it's ready for polishing in order to prepare the surface for examination. Polishing starts with silicon carbide paper lubricated with water. This first polish is on relatively coarse silicon carbide with a large grit size. And it's then taken down a series of decreasing grit sizes until the final silicon carbide polish on 600 grade paper, still lubricated with water. The specimen surface improves accordingly. The sample then goes through a polishing sequence on cloth wheels impregnated with diamond powder and lubricated with paraffin. During this, the specimen begins to take on a mirror finish. There's a series of wheels, each with a finer grade of diamond powder. And finally, the best finish is obtained by polishing on fine-grade alumina powder made as a slurry using water. The polishing debris is washed off using tap water, and the last remnants are removed by vibrating the sample in an ultrasonic cleaning bath. Once dried, it's ready for examination on the metallurgical optical microscope. Light from a tungsten bulb is collimated in a parallel beam and is then turned down the body of the microscope through the objective lens, and it's then reflected by the sample back up through the body of the microscope and through the eyepiece assembly. Here the sample can be viewed at the required magnification. This is what we see with the original bearing. The width of the screen represents 1/4 millimeter, and we can see a shiny mirror finish. It's obvious that pores can be seen, suggesting that the bearing was cast. Also, a large number of blue-grey areas which can just be distinguished from the surrounding area, which we call the matrix. This is the structure of the surface of the new bearing, prepared under identical conditions and examined at the same magnification. Again, the porosity confirms casting as a method of manufacture. Basically, it looks the same, but it does look as though there are fewer of the blue-grey areas. In order to get more information from the optical microscope, it's usually necessary to etch the specimen, and this uses liquids which attack the metal surface at rates which depend upon the chemical composition of the surface and also upon the orientation of the grains with respect to the surface. Here's a schematic view of etched grains in a sample. In this way, it's possible to highlight different grains within the sample and local changes in chemical composition, since the attacked surface reflects the incident light in different ways. This is the original bearing after etching. The dark pores are still obvious, but the etch has attacked the blue-grey areas and made them very distinct from the surrounding matrix. The matrix itself has etched to reveal gradual gradients in the chemical composition. These orange areas are indicative of a high copper content, while the lighter yellow regions suggest that less copper is there. And here's the new bearing after it's been etched. The matrix has a much more uniform appearance, and while we can still see the small blue-grey areas, there are far fewer of them. So could it be that it's these blue-grey regions that are responsible for the superior performance of the original bearing? It's well known that a successful recipe for plain bearings is to have hard particles embedded in a soft matrix. The hard particles support the load, and the soft matrix will embed wear debris and conform to local irregularities in the revolving shaft, such as occur during the running-in period. Well, have we got such a material? We can check that by using equipment like this, which is a microhardness tester. And briefly, this will bring a diamond stylus into contact under a given load to indent the surface of a metal for a given time period, and then remove the load. We will leave an indentation. The larger the indent, the softer the surface of the material. So I can select my region of interest, focus, and then bring round the diamond stylus, and I've chosen a small load to apply to the stylus. I then trigger the loading sequence, and the red light tells me that it's begun. The orange light tells me the sequence has been completed, and I can now withdraw the stylus and measure the size of the indentation left. This equipment operates with green light, but we've got a blue-grey region dead center, and in this region we can see that the indentation is quite small compared with the indentation in the matrix. So yes, we have got this type of material, hard particles embedded in a soft matrix. So it probably is these that are responsible for the superior performance of the old bearing. So although the overall chemistry of our two bearings is the same, their performances were very, very different. Etching has revealed blue areas in the old bearing which were much more frequent than in its replacement. And our microhardness tests have revealed that the blue areas were significantly harder than the surrounding matrix. So although the overall chemistry is the same, these results suggest there are variations in microchemistry. And in order to examine these, we need to go to scanning X-ray analysis techniques. In this equipment, a beam of accelerated electrons is used to scan the sample. This beam causes localized disturbances to the electrons within the sample. Some electrons are actually ejected from the surface, and others become momentarily excited to higher energy levels, and then return to their normal state. As they return, the stored energy is released as X-rays. The electrons ejected as the incident beam scans the sample can be electronically enhanced to produce this image of the metal surface. This is the old bearing we're looking at now, but this equipment can do much more than this. The wavelengths of the X-rays given off from the sample are characteristic of the types of atom present, and the intensity of a particular wavelength is proportional to the amount of that particular atom present. First, we just collect all the X-rays that are emitted over a particular area for a fixed time to obtain a spectrum for the overall alloy composition. This analytical fingerprint displays the wavelength horizontally and the intensity vertically. These peaks suggest that tin is present. The green standard marker lines for tin, which are stored in the machine, confirm these peaks to be tin. Another set of reference markers confirm that these peaks are copper. This is just an overall analysis which doesn't tell us any more than the chemical composition. But we can also ask the machine to scan the same area, but this time looking at how just one particular element is distributed within the area. Here we're looking at the analysis for tin. The highest concentrations of tin are white, the lowest concentrations black. Intermediate concentrations are represented by shades of grey. So we have a tin map for this particular area, which is about 1/4 millimetre across. We can colour code this with white as the highest concentration of tin, down through red and yellow, with the lowest tin concentration shown as blue. Remember, this is the old bearing, and the white and red areas represent the hard tin-rich particles. Here's the map for copper in the old bearing. This time the red regions indicate a high copper content. When we display the two maps together, we can confirm that the high copper regions in the upper map correspond closely to the low tin regions in the lower map. Here's the tin map for an area of the new bearing. We immediately notice that the chemistry is much more uniform. Not surprisingly, the copper map shows a similar uniformity. The differences between the old and new bearings are shown most clearly when we display all the maps together, the old on the left and the new on the right. There are still a few high tin regions corresponding to the blue-grey etching regions in the new bearing, and here's one of them. These results are only qualitative. We can get more quantitative figures by analysing a smaller area of the map. Remember, the maps are built up line by line, and we get more detailed information by analysing just a single line. Here we're scanning for tin along one line. The concentration at any particular point is displayed on the vertical axis. The tin-rich particle has approximately double the average tin content. Elsewhere, the tin content varies only gradually. If we analyse for copper along the same line, the tin-rich particle, which by coincidence now appears blue, as in the optical micrograph, is shown as having a corresponding low copper concentration. Elsewhere, the copper content is quite uniform. That's the new bearing. We can now scan a single line in the old bearing and see how the tin concentration varies across the surface. There are lots of tin-rich peaks which correspond to the large number of hard particles present. So we can be quite sure that the hard particles that occur so frequently in the superior old bearing are a result of uneven tin distribution on a microscopic level. So how did these variations in distribution occur? For a given chemical analysis, the only variable we haven't looked at so far is the method of manufacture, which in this case is casting. Most bearings are made by the process of sand casting. First, a mould box is filled with a suitable foundry sand, which is tamped down to ensure that it fills the box properly. Then a wooden pattern of the shape of the bearing we require is placed onto the sand to form the running surface of the final bearing. The bottom half is then trimmed and hardened by passing carbon dioxide gas into the sand, which contains water glass as the hardening agent. The pattern is then put back onto the now hardened bottom half of the mould. Another moulding box is added, and the tubes to form the risers are put into position. The rest of the sand is added, and the feeder through which the molten metal will be poured is formed. The top is hardened with carbon dioxide gas, and the mould is now almost complete. It's then broken down again because the wooden pattern has to be removed. The inner surfaces of the mould are coated with a mould wash. This improves the surface characteristics of the mould and prevents the molten metal from penetrating between the sand particles or eroding the sand during the pour. The organic solvent in the mould wash is burnt off to leave the mould quite dry. The wooden pattern is then removed from the top half of the mould and an ingate is carved. Once the mould is washed, the top half is put back onto the bottom half to complete the sand mould assembly ready for pouring. Under special circumstances, we can introduce metal chills at an intermediate stage during the manufacture of the sand mould. And these can be placed next to what will be the running surface of the bearing. The rest of the mould is completed as before. The top half of the mould is removed for the mould wash with the metal chills embedded in the hardened sand, ready to chill the metal as it is poured. As well as the usual mould wash, there is also a chill wash, which stops the chill from sticking to the molten metal. The mould is now ready for casting. On the right we have a completed mould without chills, and the metal is poured down the feeder tube and into the mould. When the mould is completely full, the excess material enters into the riser tubes, indicating that there is complete filling of the mould cavity. That was one without chills, and here's one which is exactly the same, but with the chills placed next to the running surface. A few minutes later, we can see that the risers in the chilled mould are cooling much faster than those in the mould box, which doesn't have any chills. There we can see the risers are still red hot. Both types of bearings, the chilled and the unchilled ones, can then be struck from the moulding box and lifted away from the moulding debris. And there we can see the complete bearing with feeder, ingates and risers. And for the one that was cast in the chilled box, we can see exactly where the chills were by the witness marks on the final product. So for these bronze materials, if we were to match the structures to the cooling rates, we would conclude that the more uniform structure of the new bearing was a result of slow cooling without chills. The metallurgist therefore concluded that the original had been cast using chills, a procedure which hadn't been followed for the replacement. He therefore recommended that the bearing be recast using chills, a procedure which was done. And several years later, they're still going strong and not showing any signs of serious wear.